Okay, today's topic is a very important topic, randomness in cryptography. So far, I used the word random many times, but now the question is, how can I create something in a random way, right? So can I create a random number? So randomness is actually a huge topic, even in philosophy. You can discuss this for hours. You can write a lot of books or read a lot of books in this topic, but we are going to focus on the randomness in cryptography. So let me give some examples. So cryptographic algorithms require random numbers for parameters like, for instance, one-time paths. We said that they have to be random. Secret keys of asymmetric cipher systems. This is important because every AES key has to be generated randomly. If you cannot generate it in a random way, then this means that you are not selecting it randomly from the whole key space, but you are focusing on a smaller subset, which actually allows the attacker to break it in a faster way, because this reduces the exhaustive search attack time complexity. Public key parameters. This is very important. In many public key algorithms, although we haven't talked yet, we say that a parameter has to be random. For instance, when you are digitally signing something, a message, for every different message, you have to choose a random number. For instance, in Bitcoin, when you're actually transferring Bitcoin, you're actually digitally signing a contract, and there actually you are choosing a random number. And this is done automatically by the software, right? But for instance, there was a bug in Java, random number generator in Androids. So some people actually transferred cryptocurrencies, Bitcoins, twice. For instance, they sent a few Bitcoins to somebody, and a few days later, using the same wallet software, they sent a different amount of money to some other account. But due to a bug in the Java, in that Android version, the random number generator actually generated the same number. If you give the same seed, it gives you the same output. It's a deterministic algorithm. But if you use the same random number for digitally assigning two different messages, we can capture your private key. And when those people did that, just a few hours later, they lost all of their Bitcoins in their accounts. Okay, so this is why it is very, very important to have random public key parameters. Okay. Also in RSA, we will say that randomly choose a huge prime number. So the question is, how can you do that, right? Session keys, they have to be random. Nonces, very important. If you use the same nonce, most algorithms can be broken. Initialization vectors has to be randomly chosen. Sols has to be randomly chosen. So as you can see in cryptography, we use randomness a lot. In almost every kind of algorithm, at some point we say that this has to be generated randomly. So let's see how we can do that. So we are going to focus on random number generators. So a random number generator produces a sequence of numbers on an interval, starting from the minimum to maximum. Of course, you choose by yourself. So think about a random number generator that produces a real number between 0 to 100. Okay. We want the RNG to have the following properties: statistical independence, uniform distribution, and unpredictability. So cryptographic algorithms mostly require random bit generators. So in our case, the min will be 0 and max will be 1, but we won't be focusing on real numbers, but integers. So the output will be either 0 or 1 because we need random bits at the end of the day. Okay, so for the rest of the talk, you can think that we are going to produce zeros and ones. Okay, so let's focus on these properties. Statistical independence. For a given generated sequence of values, a particular value should not be more likely to appear next. So what does this mean? So I have a random number generator. I produce a sequence of values. So if it is a bit generator, I produce you, for instance, a few billion bits. So just by looking at those bits, you shouldn't be able to guess the next one. The next bit will be either 0 or 1. So your probability of guessing is no different than flipping a coin, right? With probability 1 over 2, you can guess the next one. But if you look at the previously generated bits, you shouldn't have any more advantage. So your guessing probability shouldn't be something like 1 over 2 plus some epsilon. This is the idea. Okay. So for instance, you have a random number generator, and it produces the bit 1 100 times consecutively. So still you should not be able to guess the next one. I mean, you can say that, okay, this produces 1 a lot of times, maybe the next one will be 1, but still statistical independence will say that the next bit has the probability 1/2 or 0 and 1. Uniform distribution. All numbers are equally likely and none appear more frequently within the output. So this means that, for instance, if you're rolling a dice, which has 20 sides, like in the Dungeons and Dragons, then every output should have probability 1/20. Okay? This is what we prefer. Third one is unpredictability. Of course, this is generally what we want for a cryptographic purpose, right? An attacker should not be able to guess some or all of the values in a generated sequence. Because if you can do that, you can guess some parts of your secret key, right? So we can divide this into two categories. Forward prediction. Knowledge of previously generated sequences should not provide advantage to attacker when guessing the future values. Because if they somehow capture your past secret keys, and if there isn't such a property in the random number generator, they shouldn't be able to guess your future values. For instance, if this random number generator works on seeds, so if you get the seed, then you don't get the forward prediction, right? They can also regenerate everything that you are going to produce. The second thing is backtracking. Knowledge of some generated sequences should not provide advantage to the attacker when guessing the earlier generated sequences. This is also important because maybe in the past you use secret keys generated by a random number generator. You use many different secret keys, and at some point in time, the attacker get information about the current random numbers you are generating, and with this knowledge, they shouldn't be able to go back and capture your previously used secret keys, which are actually random numbers generated by your random number generator. So these are really important. But the question is, of course, how can I do that, right? How can I randomly generate a number that satisfies these properties? So generating random numbers is actually a problem. Because generating random numbers with the desired properties is difficult because computer systems are deterministic, right? I mean, these are not quantum computers. They don't focus on a natural phenomena. They have deterministic structure. So if you're running a code for a given input, it gives you an output in a deterministic way. So some people use seconds. For instance, sampling the seconds value from the system clock is a common approach for random number generation, but it cannot be used for cryptographic purposes. So I cannot stress this more because although this looks like a stupid idea, people are still using it. Okay, just get the current seconds value and use it as your secret keys. So this is the stupidest thing that you can do, but people do. Okay, so this has no. You can guess that there are limited number of seconds that a person can generate a random number in that time of interval. So you can try one by one. That's the idea. So using time between a user's keystrokes or mouse movements for an entropy source also do not provide the desired properties. So I will talk about entropy in a minute, but this is also not such a random behavior because you can also guess the time between the user's keystrokes if you can capture some information about the user and so on. Okay, so let's talk a little bit about entropy. Entropy is a measure of the disorder or randomness in a closed system. Okay. Actually, it also measures how much information something has in a different definition. So the entropy of uncertainty of a random variable x with possible outcomes with probabilities p1 to pn is defined as the following formula hx, where you simply multiply the probability with the logarithm of that probability, okay? And you sum this all over this, okay? So, for instance, the entropy will be 1 if this probability is just if you're generating bits 0 and 1 with probability 1/2, okay? You can calculate this. And this will also tell you that actually 1 bit can contain at most 1 bit of information. Okay? So this entropy is an important topic, but we are not going to focus more. I'm just giving the definition for future references. Okay, so let's focus on how can I increase the entropy or then provide randomness. First, let's focus on pseudo-random number generators. A pseudo-random number generator is a deterministic algorithm that produces a sequence of random-looking numbers using a seed value. Okay, so there's a starting point, which we call a seed value, and it uses this to generate some random-looking numbers. So pseudo-random number generators have an internal state. So after generating a long sequence of numbers, all variations in internal state will be exhausted, and the sequence of numbers will repeat an earlier sequence, because it doesn't have a infinite memory, right? It has a finite internal state. So after some point on, it will repeat itself. But of course, this can be really huge. So we can say that it is virtually infinite and it doesn't repeat itself. Yeah, periodicity can be very large so that it would look virtually infinite. For instance, if your periodicity is 2 to the 200, then you will never generate 2 to the 200 bits, so you will never see this periodicity, right? Same seed provides the same outputs. Hence, this property can be used for reproducibility. This is important, and this is what I use generally. So I generally need some random plain text, for instance, to check my cryptanalysis results. So I use a random number generator with a seed to generate all of those random numbers and use it as a plain text and perform my experiment. So this is important because if somebody wants to reproduce the same results of the same experiment, I can simply give them the seed value and they can regenerate all of these maybe terabytes of data from a single seed value. So this is the good thing. But the bad thing is that if the attacker captures or guesses the seeds or the internal state, then the security is lost, because at that point, they can also generate the same numbers, right? So I will come back to this when I talk about random number generators in the Intel CPUs, okay? Yeah, I mentioned them as the pseudo-random number generators because they weren't truly random. So question is, what is truly random? To avoid deterministic nature of pseudo-random number generators, true random number generators use a physical source to generate random numbers, because randomness is in nature, okay? You can get the sampling from the nature and then, do some randomness on them. For instance, the physical source in this scenario is called an entropy source and can be physical phenomena like radioactive decay. Think about it. Here, I put a radioactive material on the desk and measure the decay, and then produce zeros and ones depending on this decay. Since I cannot predict how it is going to decay, this can give me some information. So this is called the entropy source, and the data I gather from it is the, I will call it entropy pool and use it somehow, which I'm going to talk later. But as you can see, this is physical phenomenon. Or you can use thermal noise, shot noise, avalanche noise in Zener diodes, clock drifts, but of course, if this can be guessed, can be susceptible to timing attacks, timing of actual movements of a hard disk read-write head. Of course, this is currently no longer that's possible, because if you're using an SSD, you don't have a optic stuff, right? So that goes from one part of the hard drive to other part, because the timing will be different in that case. In the SSDs, we access the data in a lot faster way. Or radio noise. As you can see, most of this stuff are actually on a board. You can measure the physical phenomena like the heat or the noise, these electronic parts produced by the device, okay? But since it is from a natural phenomena, it works like an entropy source, okay? But the thing is that due to their nature, these true random number generators does not provide uniformity property, right? Because if I'm focusing on the radioactive decay of a material, I cannot prove that it is going to produce zeros and ones in a uniform way, right? Because radioactive decay is not that uniform. Or similar thing is for thermal noise and so on. But a hash function can be used to overcome this issue, right? So IDs have a physical entropy source, gather data from it, put it in a large file, and whenever you want to generate a random number, don't use this data directly. Put it as an input to a hash function and use the output as your random number. So this way you can get the uniformity property, right? And also, true random number generators are not as fast as software and hardware solutions, right? Because if you want to generate a lot of random numbers in a very short time, you cannot just wait for a material to decay, right, in a radioactive manner. So idea is to combine them. So these are called cascade construction random number generators. So modern operating systems and cryptographic libraries generally take input from an entropy source to supply a buffer or pool of entropy. Then it is used periodically to see the cryptographically secure pseudo-random number generator, which is shortened as CSPRNG, to provide random numbers. So let me show a picture. So this is actually how it works. You have an entropy source, okay? You gather data from it and put it in a pool. Then perform a cryptographic function on it to produce random numbers. So let me give an example on Linux. So whenever you turn on your computer, actually, Linux operating system, accesses some files, right, when the computer boots up. So this info, which files you are accessing and that order actually taken as an entropy source. But after the operating system boots up, you start to, press on some keys, move your mouse. So these are also taken as entropy source. And all of these data is gathered in a file on the hard drive, for instance, at most 4 gigabytes, let's say. So initially it is empty, but by getting all of this information, you are putting data in this 4 gigabytes. Well, of course, if it exceeds 4 gigabytes, you remove the initial data and put the latest data. It is like first come, first out kind of access. So this is here you most of the time have a pool of data gathered somehow from natural entropy sources, but generally it is not that possible. But at the end of the day, you have a pool of data coming from some sources, okay? So whenever you need the random number, for instance, you are visiting a web page and you want to generate a random number, for instance, for your Diffie-Hellman key exchange, or you want to generate an AES key. So you can simply apply SHA-256 on this entropy pool to get a 256 random bits, right? And you can use it as your AES key. And at this point, you're hoping that nobody will be able to have the same entropy sources to provide the same entropy data and have the same entropy pool, and then perform the hash function and obtain the same result. Okay, so if you are getting the data from the nature, then this cannot be done, right? Some people have different ideas. For instance, put a camera, especially old ones, old mobile phones, which has, when you take a picture, has a lot of noise, right? Put it in the same room, take a picture, but all the time the noise will be different due to lighting and so on. And you can use that information, for instance, as an entropy source. You can come up with many different ideas. Okay. So cascade construction random number generators. This method is faster than true random number generators. But since the implementation is in software, it is vulnerable to memory-based attacks because you're keeping some data on the memory. Timing attacks. It also doesn't solve the problem of what entropy source to use. Sampling user behavior is not that secure. Your mouse movements and so on can be guessed. Here, there was for instance, a type of attack that is suggested in literature. For instance, as I mentioned, that when you boot up your operating system, this entropy pool is empty, right? It is started to be filled after your computer is turned on. So initially, the entropy is not that high because it is empty. So if you can force somebody to restart their computer and instantly generate a random number when it boots up, you can pretty much guess what that random number will be. It will be easier than to perform a brute force attack.